Hello again, chemistry students. This is the third video. This should be 3 of 3. I don't think we'll need to make another one. So just to review quickly, we are answering one question still. And this question has 4 parts to it. So this is all the work we did before. Okay, so here's a question. So part A. Let's erase some of this stuff here. Our first point, we calculated the pH of a weak acid strong base titration. This pH part A is for before the titration has started. So before any base has been dropped into acid, we used a simple acid equilibrium problem or like problem to solve for pH at our first point. Then at the second point, titration has started. We've introduced 10 mils of sodium hydroxide at that concentration, and therefore that required 2 parts of the calculation. So we needed a stoichiometry part to figure out how much acid is left over, and then from there we used a bit of equilibrium, a nice table to solve for the concentration of hydrogen ions, and then from that we can figure out pH. So these two were done. Okay, so that left us with a roughly drawn right now with a titration curve that looks something like this. Okay, a pH, I believe it was 2.62 at our first point A, B after titration, but before equivalence, I think that was 4.74 if I'm not mistaken. Then at equivalence is what we're going to figure out next. So this is C, and then beyond equivalence is D. Now, D didn't give us any information about how much beyond equivalence. So I'm going to make a number up. I've pre-calculated something. And well, I think it's 3 mils I chose, so just 3 mils past equivalence. We're going to figure out what the pH is for that. So we're going to do these 2 points for this video. Let's get started so it doesn't take too long. Okay, third point, at equivalence. So at each of these points, I suggested it's a good idea to always try to think about what ions are present. So in our third point at equivalence, we know that acid has been completely consumed, so there is no more acid. So HA does not exist anymore. In this case, HA is acetic acid, so there's no more HA. There is also no more hydroxide ions because this has completely neutralized acid. These two don't exist. So what's left is our neutral ion from sodium hydroxide, right? Sodium ion. And of course, this doesn't affect pH, so we can ignore that. So what's really left is our conjugate base, acetate, and water. So again, when these two, if you recall, a few lessons ago, we did acid or acidic and basic properties of salts. When a conjugate base came from a weak acid, that means in this case acetate. When that is present with water, it behaves like a base, right? So I'm going to show you the expression for the hydrolysis of this acetate conjugate base ion with water. Here it is. Okay, so our acetate ion behaves like a base. You will see that it will, according to the Bronsted-Lowry definition, will take up a hydrogen ion and it will become this. So here are our conjugates here. So this behaves like a base, right? This will be a conjugate acid. Water in this case is behaving like an acid because it is donating a proton. So that's that, and its conjugate is right here. And this, of course, is going to be our conjugate base. Okay, there is an equilibrium expression we can write from this. Products over reactants, we can ignore water, and we have our conjugate, rather we have our Kb expression here. Okay, so we, again, remember, we're trying to figure out what pH is at this point. So looking at this expression, right, if we figure out the concentration of hydroxide, we can figure out pOH, and once we have pOH, we can then figure out pH. Okay, but we don't have, the question gave us a value for Ka, but it didn't give us a value for Kb. So this is how we start to solve. So we can figure out what this Kb value is from our Ka and our Kw values. And this is the relationship here. So I'll ignore this for now. Ka given to us in the question. We know our equilibrium constant for water, Kw, 1 times 10 to the negative 14. And of course, this is the relationship we have between Ka and Kb and Kw. We do a bit of grade 9 math here, solve for Kb, and we get Kw divided by Ka. Okay, 1 times 10 to negative 14 divided by 1.8 times 10 to negative 5. And look, we have our Kb value. Okay, so now that we have that, we're one big step closer to starting to solve this. But remember, we've added at this point, I believe it's 20 mils. Right? We've added 20 mils of sodium hydroxide to the original 20 mils of acetic acid. Whenever you change volume, you also dilute and change concentrations. So to reach equivalence again, we've added 20 mils for a total of 40 mils. Now remember that calculation we did in the last video where we calculated how many moles of acid we have, and since it dissociates in a 1-to-1 ratio, we can also therefore say we have that many moles of conjugate base, or acetate ion. Okay, so we have this number of moles of acetate ion, right? We have a new volume, so we can figure out what our new concentration is, right? This concentration, if you recall, is N divided by V. Moles divided by volume. Okay. So with this information, look, we have Kb. Okay, we have concentration, the concentration of our acetate ion. When in doubt or not, always write an ice table. Right, so initially we have, at this point, initially, meaning at this point we have acetate present with water. Before it hydrolyzes, before it reacts, we have none of our product, right? We have a certain concentration now of acetate ion. We know that this is going to decrease by a factor of x. We say minus x, and these will increase by x plus x in each case. We have our expressions at equilibrium. So I plus C equals E, 0.15 minus x, and we have these expressions here, these values, x and x for our products. Remembering that Kb has been determined to be that. Right, really small Kb value. Keep that in mind. So we can plug things in. We know we have an expression for these two, right? For our products, we have an expression for our reactant. Plug those in. It's really just x times x. We get x squared. Our expression for acetate is 0.15 minus x. Now, since the 100 rule applies, we can get rid of this minus x. You don't, again, have to show that, prove that the 100 rule or the 5% rule applies. You do have to state it, though. Okay? You can't just get rid of things and move things around in math. You have to provide reason for it. So this is our reason. We provided it. Again, we don't have to prove it, but there it is. Now, solve. Look here, we've eliminated that x. Now solve for x, cross multiply, square root, and we get x is equal to 9.2 times 10 to the minus 6. Now think about what this means. Going back to our ice table. If we've solved for x, that means we have figured out the concentration of hydroxide ion, which is another big step closer to finding pH, because with pOH being the negative log of the concentration of hydroxide, we get 5.05. And of course, the relationship back to grade 11, just to review, the relationship between pH and pOH is this. pH plus pOH is equal to 14. So once we know pOH, we can figure out pH. It's just 14 minus pOH. We get 8.97. So that's therefore the pH. That's a pH at equivalence. We now have our third major point. Okay, so think about what indicator might be good to use. I'm going to give you the answer here. Phenolphthalein. Phenolphthalein is a great indicator. Change color that's slightly just above a pH of 7. I think it's 8.2 approximately. So it's a great indicator to use for a weak acid, strong base titration. Okay, now beyond equivalence. Now I think I just made up a number here. So with 3 mils of base going over our equivalence, we're going to calculate pH. Okay, so this is how we do it. I'm going to switch screens here. I'm going to open up my ink pad. Okay, so pH after or beyond equivalence. Okay, remember, so recall 20 mils of NaOH was required to reach equivalence. Now, at 23 milliliters of NaOH, right, this means we've exceeded equivalence by 3 milliliters. So let's figure out how many moles we've gone over by. Okay, so moles of NaOH is C times V. We know that we have a 0.3 molar concentration of base given to in the question. We also know that we've gone over by 3 mils. So this is just 3 mils, divide that by 1,000, we get 0.003 liters. Okay, because you have to convert to liters. Look, liters cancels out. And we're left with 0.0009 moles of NaOH. Okay, now since NaOH dissociates in a 1-to-1 ratio, okay, therefore the number of moles of OH is equal to the same thing. If we weren't using sodium hydroxide, so if you were using some other base, we would still have to take this dissociation into account and make sure that it's 1-to-1, and if it wasn't, then we have to make that stoichiometric adjustment. Okay, now just like in the past, whenever you change volume, you therefore change concentration. So now we have the number of moles, but we have a new volume, right? We have our total volume is now 20 mils of acid plus the 23 mils of base for a total of 43 milliliters, or we convert that to liters and it's 0.043 liters. Okay, so our new concentration of hydroxide ions is 0.0009 moles, right? Moles divided by volume, divided by 0.043, and we get 0.02093 moles per liter. Remember, try to keep at least 4 or 5 digits, or use the answer or memory button in your calculator whenever you're doing these calculations, only round at the end. Okay, so that's a concentration of sodium hydroxide, rather of hydroxide, to be specific. Okay, so that's an important number because now we can take that and plug into, nope, not our pH, let's erase that. We can take this concentration, plug that into, right, our pOH, which is negative log okay, which gives us 1.679 is our pOH. Probably should have included another digit here. Okay, so to find pH, we know it's 14 minus pOH. We know what pOH is, so we just plug that in, 14 minus 1.679, and we end up with a pH of 12.3. And we're done. That's our fourth and final point. Now, what will often happen in questions like this is you'll then be asked to draw, and I know this is the case for your lab, you'll be asked to draw a titration curve. So hopefully I do this. Let me take out a ruler. This worked last time I tried. Okay. Not there. Here. Okay. Move my ruler around. Okay. So pH, volume, right? Don't forget it has a characteristic spike, then gradual increase. This is your buffer region, right? Then it goes up suddenly to your equivalence, and then beyond your equivalence, it plateaus, right? So we know this point, this was A, and I believe it was 2.62. Then at 10 mils, we calculated a pH of 4.74, I think that was. And then at your equivalence, what did we get? I think it was 9.7, right? So this was B, this was C, okay? And this was at 20 mils. So only slightly above, maybe my graph isn't perfect here, but only slightly above. So let's say here, so at 23 milliliters, so just 3 mils beyond equivalence, you can see the sudden jump from 8.97 all the way to 12.3, to a new pH of 12.3. This is your last point. Okay, so this is a titration curve so the titration of not and with. Okay, good. That's it. Back to our lesson. Okay, so we've completed that. That was one question. Here's some extra practice. I will post more solutions online with more examples. Again, the only other, right, so that's your home fun here. We will continue to practice. This is your homework, right? I do have some more practice posted online, but concentrate on this. The only other way that this question can get a little more challenging, and it will, and I'll show you what to do to solve that. I've already given you some clues along these videos, is in this question, it gave you exact volume measurements for each of these points, right? Of course, not the first point, but look, it gave you a volume measurement for here. It gave you a volume measurement for your equivalence. So those are instances that makes this, or this is information that makes this question a bit easier. I don't know if you can imagine. Now, if you are not given these, specifically equivalence, actually specific to your equivalence, if you're not given this value, there's one more small step to add, but I'll post videos or solutions for that. I hope this helped. It is very important for you to practice and then to ask questions. So go over these lessons, practice, ask questions, and you'll see it's not too hard. It just takes you, of course, some effort. Okay, hope this helps.